Okay, so now it is recording, and so now let us just continue. So now let us now go through the actual content of this chapter, which is the common source amplifier. And just to go through it, it is that you are just applying your input at gate, sensing your output at drain end, and this V in we intrinsically are assuming here that it includes the V bias and the small signal that you are intending to amplify. And it is the device here. Obviously, if you are talking about amplifiers here, we are always talking about saturation. So you have multiple choices of load here, right? That are across what kind of load would you want to observe this V out. So we know that for resistive load, what you're basically just doing is that instead of this load guy, you're just inserting some resistor, and then you have this your transistor, and now you're sensing your output here. And the fundamental problem with this resistor is the Ohm's law drop or IR drop. That is, we know that the condition for this guy to be in saturation is that V out is greater than what? Vn minus Vt, right? But the problem here is that if Vn increases, the current will also increase, right? Because we know that as Vgs increases or Vin increases, current will increase, right? The bias current typically will increase. And what will happen is that here, the bias output voltage, because I hope you already know that V out is also is basically equals to V out bias plus the small signal V out, which is the amplified version of small signal V in. So the problem here is that if the current is too high, the resistance can drop the value from VDD to such an extent that it can go out of saturation, right? Because this V out, this bias value, to be honest, is what V out is equals to VDD minus IR. And if this I keeps on increasing, it can clearly become low enough so that it falls out of saturation and this condition is violated. So resistance, this sets the fundamental limit on what value of resistance you can choose. So this is kind of a bad situation for us because if we want to increase the gain, we would want to increase the load resistance R, but we can't do that much, right? Also, one more thing that we must realize is that, yeah, in small signal, there is an R out also which goes in parallel with R, and you will say that, okay, it will be combined resistance, but typically R will be much, much less than R naught, right? So, because if you want resistance to be large as R naught, resistance also has to be basically large in size, which will again consume your area on chip. So, taking a resistive load is not a great idea, right? So, there are two reasons. One is that IR drop, and another is the area concern. So using resistive load is not that great of an option for the CS amplifier. So basically what we are doing here, as it is also in the content of Razavi, that we are basically talking about the CS amplifier, and we are just trying to explore that what can be the possible load options for this, and that in its own self becomes a standard circuit. Okay, now that we have discussed this, I think we already know that the gain of this guy should be equal to what? If we can follow the lemma, or you can also just follow it, just calculate it by intuition, is that see, source is grounded, you are applying V in. If source is grounded and body is grounded, so body effect will not come into picture for this particular circuit. And so the gain will be directly what? Minus GM times whatever this load is here, parallel R out. I think that's not a big issue to find why it is happening. So, and why is this minus sign coming? Can you comment why this minus sign is coming intuitively? Because when you solve it in small signal model, you just find it out yet. Yeah, minus sign is coming, but why really minus sign is coming here? Can you comment on that? So, what is the intuition behind this minus sign? Like, yeah, when you solve it, you'll find that a minus sign comes into picture, but what's the intuition? So we'll get into that. And meanwhile, if anyone is watching it, I'll encourage to think about what's the basic intuitive reason that why the minus sign is coming into picture there. Okay, so so let's go to the next option that we have instead of a resistive load. What can we use? Which is a current source load, so, which is basically using a transistor. And the idea here is that if a linear device like resistor is causing a huge drop, so why not just use a non-linear device which is not causing that kind of a IR drop, like a transistor? So the thing here is that transistor will allow bias current to flow normally for bias voltages, and when small signal current is concerned, it will also offer high impedance. So it is a win-win situation for us, right? Because if I'm just biasing this load and I'm connecting some circuit here and I'm sensing my output here, so it will allow my bias current to flow for some value of VDS, right? And obviously the VDS should be set such that it is in saturation, but again the IR drop will not be that terrible as will be in the case of resistor. And for small signal, again I'll have some good impedance also for my small signal for amplification, which you already derived here, that here if it is in saturation, it is basically acting like a current source only, right? And I'll have my R out amount, R out not amount of resistance, which again is quite great for us, right? So this is the merit of current source load. But again, we are talking in terms of amplifier design, like if let me just draw the circuit once, which is VB, and this is my basically current source load, and here I have my CS amplifier, and here I have my V out. So the idea here is that yeah, it will offer R out impedance, and so the gain will be GM R naught by 2, because R naught and R naught come in parallel, provided these two devices are have identical R naught, which is typically not true, but here we are just approximating. And the idea that I want to convey here is that this transistor basically needs what? It needs a minimum VDS so that it remains in saturation, right? And we know that if this guy is VDD, so the output has to be how much? Output has to be at least VDD minus what? Output has to be at least VDD, or it can be at most rather, because if this increases, this VDS drop will decrease, right? So it has to be, it can be at most what? VDD minus VDS or VST rather, since we are talking about PMOS of load or M2. So this is the basically output upper limit, right, on the swing here. Similarly, on the lower swing, or the lower swing limit is set by this transistor, where it requires that this drain voltage must be at least greater than Vn minus Vt. So this is the lower output limit. This is the problem of output swing, right? So here again, when it is a problem in design that you have to bias the transistor such that it's in saturation, and this thing is called voltage headroom, and the voltage headroom consumption is such that our output swing is in acceptable range. For example, if this upper value that output can achieve, say that this VST is too large to maintain this in saturation, so this means that output can't swing to a very high value. And if this guy is also very large, this means that output can't even swing to a low value. That means that output can't swing much at all, which basically kills the purpose of amplifiers. This is the output swing problem. That basic idea is that your output is swinging from certain value to certain value, but the swing should be such that the amplifier action and the action of the load and their intended bias points are preserved. So this is a problem that we encounter in analog design, and thus we have to be quite mindful when designing and sizing circuits. Great. Let us move to the next load that we have, which is the diode connected load. So I'll just again draw this. So this was discussion about the current source load, and now I'll just like to elaborate on diode connected load. Again, here I'm just talking about NMOS common source, and you are free to explore PMOS common source here. Then we'll be just drawing it for NMOS load at the pull down path. So it is basically more or less the same thing. Here you have your V out. Here you have a common source. So here again, this guy is always in saturation, and the impedance that is offered by this PMOS was approximately equal to 1 by GM. So here also you have some resistance, right? R naught, and these two guys again parallel are approximately equal to what? 1 by GM. So the gain that basically we get here is what? Minus GM 1 by GM2. Again, if you are to solve this guy full-fledged solution, so the answer will not be exactly this. But again, we are doing it by some intuition, some approximation, and thus this is all in order. And this the idea is to not just do brainless maths again and again, but to get an idea and intuition as of how equations work out. Okay, so this is the gain here, which is cool, which is all right. But what is the voltage headroom consumption here? That idea is that, see, this guy is always in saturation, right? This guy is always in saturation, which means that the which means that am I now fundamentally limited in my choice of my headroom, like in my output swing? Let us think about it. See, V out is coming here. I'm talking about large signal. So the condition for this transistor to be on is that V out minus VT must be greater than what? This is PMOS, by the way. So I should write it differently. I should write it as 0 minus V out minus Vt must be greater than 0, right? Because it is basically VSG minus Vt, right? So this basically implies that my V out must be what? My V out must be, or V out plus Vt must be less than 0. Doesn't this guy imply this? This also implies that my upper limit of V out must be less than minus VTH. Isn't this a very strange thing that the upper limit of V out is limited in this way? Hmm? That if I want the upper load device, diode current device to be on, this condition must be satisfied. Doesn't this seem very weird? But this, by the way, this circuit is also used a lot. So I'll encourage you to think on this problem, and I'll encourage you to think on this problem. And this is one of the problems with diode connected load is that the voltage headroom consumption here is more. Is it more or not more? That is something that I would encourage you to think about. Maybe we'll go through it at the end of this video. But yeah, now for active load, now there's another configuration that goes by the name of active load. So I'll just draw it out here. The idea here is that load is typically passive in nature. What it means is that you're not feeding it any input. The load is not basically itself being fed an input, but here what we see, and the load has no amplifying action. That is the basic meaning of passive. But here what we see, this is PMOS and this is NMOS. You think you can recognize this as a CMOS inverter. What basically happens here is that this guy, or you can say alternatively this guy. So this is common source and this is also common source, and here you are seeing your output. I'm not specifying the circuitry for biasing, or typically you need a resistor here to bias this guy, but I'm not basically drawing this for simplicity. So the thing here is that if you're saying that this is my reference NMOS, which is in CS, so this is the active load. You're saying this is my reference PMOS in CS, then this is the active load, right? Because the load part also is being fed current. Now, if you can really observe, there's a symmetry here. Why? Because in small signal model, and if these two MOSFETs are identical, or even if they are not identical, nonetheless, what you can realize, which I'll just draw here separately, is that they'll have some R naught P. This guy will also have some R naught N, and it will have some current, right? It will have some current here, and it will have some current here, right? And here is your input, and the current and the output is basically over here. So in small signal, this guy will get grounded, this guy will get grounded, this guy is also getting grounded. So you can understand the kind of, I can fold this guy about this line of symmetry, and the transconductance will then therefore add, and the impedances will get in parallel. So the expression basically for gain becomes GMN plus GMP multiplied by R naught 1 parallel R naught 2. And if you're considering the body effect, which body effect will not come into picture here because these two terminals are grounded, so VST will not come into picture. But if you're considering the body effect, which body effect will come into picture here because these two terminals are grounded, so VST will not come into picture. And if you're considering the body effect, I think that the recording is not getting recorded properly. Let me just check. I think, yeah, recording is being recorded. So, okay, everything is fine. Okay, great. So, this was the discussion on active load, and then we have something by the name of triode load. Okay. So what we intend in triode load is that we try to make the MOSFET work, the load MOSFET work in triode regime. That means that we set its bias point such that it's in triode regime. And we already derived above is that when the pull-up path is in triode regime, the resistance comes out as 1 by GDS. And that is also a possible configuration that you can use. And what we find is that the triode load consumes lesser voltage headroom and diode load consumes more voltage headroom. And it is the problem here is that to generate such a precise bias voltage for the load that it is in deep triode region is hard. Now, I think it is very much in order that I now discuss the problem that I posed you before about the voltage headroom consumption and diode load. And let us just compare it right away. Okay, so let me take this guy, VB. Here is my CS stage, okay? V out. Here is again my VB, and this is the CS stage, and this is my current source load or saturation. This is my triode, and which is basically the deep triode load, and this is my diode connected load. So let us just answer the question which I like hinted on before, is that which of these loads is performing best for voltage headroom. So what we mean by basically voltage headroom is that if I have some voltage level V plus, V minus, so this is the headroom, right? If I am saying that my output can swing from here to here, so this is the headroom, that how much output is being able to swing, right? And I just already discussed earlier also that this load needs a certain drop VDS to be able to be in a certain bias point. For example, to be in saturation, this VDS value must be equals to what? Or VST value, I'm just talking about magnitude here, but whatever. Anyways, the magnitude of this VDS must be at least be equal to VD sat, right? Which is equals to what? VGS minus VTH, right? So this is the minimum value this guy must have. So this is the minimum headroom it will consume for saturation. So the same thing is true for here also for diode connected load, that this guy must be at least of this value, correct? Whereas, so that means that this much drop is happening, and so the upper output swing is limited, right? Because what I'm trying basically saying is that if this signal V out, if it swings all the way to VDD, right? If my V out is swinging all the way to VDD, then this VDS, this there has to be like what I'm trying to say is that if is my reference level, my V out is swinging here, I want some VDS also to be available, right? If this is my VDD, so that these two guys are in saturation. But if my V out is swinging all the way to VDD, these two guys won't remain in saturation. This guy will become off, and this guy won't remain in saturation. So that's the idea, that if you are having your loads in saturation mode, your output upper swing will be limited. But that's the sacrifice we have to make. In triode load, this guy consumes lesser voltage headroom. And I think you should be able to comment on why is that so, is because it's in deep triode, which means that VDS or VST value is already too low, right? The value is too low. That's why it is in deep triode to begin with. So that means that my output can swing higher. My output can swing higher because here the VST value is lesser, right? So that's the basic idea. And that's what I have already written as a point of reference for me, that in triode load, the voltage headroom consumption is less, but the generation of VB or bias voltage is hard, which is also hard for current source load, that this bias voltage generation is typically hard for us. And here, more voltage headroom is consumed, which is a problem for typically for any saturation based load, right? But again, in diode connected load, if I revisit that example, the freedom also is not there, right? Because these two terminals are basically shorted with each other. So on the basis of the output swing, the VST is the minimum VD is decided, so the output is fundamentally limited. But here you can still like maintain it in saturation and like change VB a bit, tune it so that you can maybe get a bit improvement in your voltage headroom. So that is the basic thing to be said there. And now let us now talk about one of the most important configuration here in CS, which is common source with a degeneration. So what is the thing happening here? It is common source with degeneration. It basically means that you have your certain amplifier, you have your common source amplifier. Here I'm drawing a resistor, and pardon me, it is just for simplicity. The thing you are doing here is that you're putting a degeneration resistor over here, right? And here is your RS. And this is your common source degeneration. And I think I'll elaborate more on this in the next clip. So yeah, so thank you.